So in Module 4, we are going to look at quadratic relations. In Module 3, we focused on all polynomials and looked at all of them. But now we're going to look at specifically the quadratic ones, so the ones with the x squared as their biggest term. And before we really get into that, we need to start by discussing complex numbers. So we already discussed in Module 3 that how to simplify radical expressions. We know the square root of 16 is 4, because I can break that down as 4 and 4, and I have a pair of 4s. And in the beginning of Module 3, we looked at an example where we had a negative underneath the square root. And we talked about, well, I can't do the same number times itself. Negative 16 is negative 4 times 4. There's no way to get two numbers that are equal to multiply to a negative number under the square root. So we said that we were not able to simplify these because these are what we call, this is a not real number. Okay. So the complex number set allows us to simplify allows simplifying of negatives underneath a square root. Okay. And you may have seen imaginary numbers before. So we let the letter I represent negative numbers underneath square root. So I specifically represents the square root of negative 1. So now that we have discussed this, we can now simplify negatives underneath the square root. In our first example, we have the square root of negative 16. So I can rewrite this as the square root of 16 times the square root of negative 1. I can kind of separate the negative part. And we already know how to simplify 16, 4 and 4. And now that we've discussed that the square root of negative 1 is I, it simplifies to 4i. We can do the same thing with the square root of negative 21. So I can already bring out the negative and write it as I square root 121. And 121 is 11 times 11. So then I get 11i. But what if I don't have a perfect square? For example, the square root of negative 28. So I'm going to separate it. I'm going to first rewrite it as I square root 28. And now I'm going to simplify 28 like we did in Module 3. So 7 and 4. 4 is 2 and 2. I have my leftover 7. So it becomes 2i square root 7. It can also work if you have variables underneath the square root. So I'm going to first simplify it as I square root 64 x cubed y squared. 64 is 8 and 8. So it's going to become 8i. Now I'm going to simplify my variables like normal. I have one group of 2 in x cubed. I have one group of 2 in y squared. And then underneath, I only have the x. Now, technically speaking, I could put that I at any place in front of my square root, but I typically like to keep it with the number. So 8xyi doesn't really roll off the tongue as well as 8ixy. So that's why we usually place it next to the number and not after the variables. We also have exponents for I. So we're going to look at multiplication in a little bit. And we are going to be dealing with powers of I. So we have to discuss how raising I to exponents works. So let's start with I squared. So if I'm going to write I squared, I can think of it as the square root of -1 squared, because I is square root -1. And we know from Module 3 that when you square a square root, it cancels. So when I square I actually end up with -1. So I square I no longer have an imaginary number, basically. All right. What about I cubed? I can break that down as I squared times I using my rules of exponents. I know that when I multiply with exponents, they get added. So I squared times I is I cubed. We now know that I squared is -1, so I cubed is the same thing as -I. And then lastly, we have I to the 4th. So I to the 4th, I can break it down as I squared times I squared, which becomes -1 times -1, which is 1. After I to the 4th, all of the powers of I repeat themselves. So I to the 5th, if you break it down, so for example, I to the 5th, I can write that as I to the 4th times I. And we just talked about the fact that I to the 4th is 1, so that just becomes I. I to the 6th is the same thing as I squared. I to the 7th is the same as I cubed. I to the 8th is the same thing as I to the 4th. So the powers of I are what we call cyclical. They repeat after a certain cycle, and that cycle is exponents of 4. Let's now discuss operations with complex numbers. So it's very similar to operations with regular polynomials and radical operations as well. So if I have 3i times 4i, similar to when we're multiplying radicals, I'm going to do 3 times 4, which is 12. And when I do I times I treat it like a variable, I get I squared. Now, important thing to remember, I squared is -1. So this becomes 12 times -1, which is -12. So it is possible to multiply two complex numbers and get a negative number. Okay. Next, we have -3i times 9i. Well, -3 times 9 is going to be -27. And then I'm going to get I squared. I squared is -1, so it becomes -27 times -1, which is positive 27. Your final answer when multiplying with powers of I should never contain I squared. You have to simplify I squared always. Now let's talk about addition and subtraction. So just like with polynomial addition and subtraction, you're basically just combining like terms. So the real number portion and the imaginary portion are the like terms. So 2 plus 3i plus 3 minus 8i, the 2 and the 3 are like terms, so they add to 5. 3i and -8i are like terms, and they're going to add to give us -5i. And I can't simplify just I. There's no point in replacing I with the square root of -1, so we just leave it as I. With subtraction, again, I'm going to treat it very similar to when we were subtracting polynomials. My first step is to distribute that negative into my second set of parentheses. So it becomes 12 minus 7i minus 3 plus 2i. And now I do the exact same thing with addition. I combine like terms. So 12 minus 3, which is 9, and then -7i plus 2i, -5i. Next, we have multiplication, where we have two sets of parentheses with addition and subtraction. So just like with polynomial multiplication, I'm going to distribute. Everything in the first set of parentheses is going to multiply to everything in the second. So 2 times 4 is 8. 2 times negative 3i is negative 6i. I times 4 is 4i. And I times negative 3i is negative 3i squared. So now I have to do two things. I want to combine like terms, and I want to simplify powers of I. So that means replacing that I squared with a negative 1. So I'm going to get 8. Negative 6i and 4i are like terms. So I'm going to get minus 2i. And once I replace the I squared with negative 1, it becomes negative 3 times negative 1, so it's going to become plus 3 at the end here. And then 8 plus 3 is 11. Like terms there, I get 11 minus 2i. Okay. Now I have 5 plus 2i times 5 minus 2i. So again, everything in the first set of parentheses multiplies to everything in the second. So 5 times 5 is 25. 5 times negative 2i is negative 10i. 2i times 5 is positive 10i. And then 2i times negative 2i is negative 4i squared. In this example, my negative 10i and my positive 10i are going to cancel. And once I replace my I squared with negative 1, I get 25 plus 4, which is going to give me 29. This example is very similar when we were multiplying radicals and we were multiplying by its conjugate, and the radicals canceled, and when I multiplied it square root by itself, it canceled and I just had a number. It's very similar with complex numbers, which now leads me to division with complex numbers. It's very, very similar to division with radicals. So just like how we can't divide by a radical, we also can't divide by an imaginary number. What does it mean to do 5 minus 3i divided by I? How do I divide by the square root of negative 1? So we do something very similar where we multiply by conjugates. So instead of multiplying the top and the bottom by the square root, in the case of i's, we multiply the top and the bottom by negative I. And I'm going to tell you why in a second through this example. So I'm going to treat this 5 minus 3i as a set of parentheses. So I'm going to have negative 5i plus 3i squared over I times negative I is negative I squared. Now I want to simplify powers of I. So I end up with negative 5i minus 3 in the numerator, and my denominator becomes 1. So the reason I chose to multiply by negative I instead of positive I, I'm going to show, and then just to finish simplifying, I end up with negative 5i minus 3. Now, typically speaking, when we write complex numbers, we like to have the real number come first and the imaginary come second. So I'm just going to reorder this to be negative 3 minus 5i. They're the exact same thing, and I'm not going to take off points for it on an assignment or an assessment if you write it in the other way. This is just the more common way. I'm going to do the example a second time, and this time I'm just going to multiply by I in the numerator and denominator. You're still going to get the exact same answer. It's just one more step is involved in the simplifying. Well, not necessarily one more step, just a little bit a more difficult step. So I'm still going to distribute, but this time I'm going to get 5i minus 3i squared all over I squared. Okay. And when I replace my I squareds with -1, I get 5I plus 3 all over -1. So the purpose of multiplying by -I instead of just I over I is so that I don't end up with a negative in my denominator. Because you don't say 5I plus 3 all over negative something. When you read a fraction, you don't say 1 over -2. You say -1/2. You usually say the negative first. So now when I divide by my negative, I still get -5I minus 3, which is -3 minus 5I. So I still get the exact same answer. It just eliminates me having to divide by a negative, and now I can divide by a positive number instead. So that's why we multiply the top and the bottom by -I. That way we don't have a negative in our denominator. So what happens if we're dividing and we don't have just I in the denominator? Like we have in our next example, 5 plus 8I all over 1 minus 2I. Very similar to when we had addition or subtraction in the denominator with radical, where we multiplied by its conjugate. Here, we're going to multiply by its complex conjugate, which basically just says the conjugate of a complex number. It works the exact same way as a regular complex conjugate. It's just the opposite operation of what's in the denominator. So the complex conjugate that I'm going to multiply my numerator and denominator by is 1 plus 2I. It does the exact same thing when we were rationalizing the denominator with radicals. It gets rid of the imaginary number. So my numerator, 5 plus 8I times 1 plus 2I, all over 1 minus 2I times 1 plus 2I. And just like with the radicals, I have to multiply everything in the first set of parentheses by everything in the second, in the numerator and the denominator. So 5 times 1 is going to give me 5. 5 times 2I is 10I. 8I times 1 is 8I. And 8I times 2I is 16I squared. In my denominator, 1 times 1 is 1. 1 times 2I is 2I. Negative 2I times 1 is negative 2I. And negative 2I times 2I is 4I squared. Just like when I was multiplying with radicals, I'm now going to combine like terms in my numerator, and I'm also going to simplify powers of I. So I'm going to get 5 plus 18I, and then my positive 16I squared is going to become a negative 16. In my denominator, just like when we did the rationalizing, my plus 2I and my minus 2I are going to cancel. So now I have 1, and my positive, oops, that should be a negative. This should say minus 4I squared. The minus 4I squared is going to become a plus 4. When I finish combining like terms in my numerator, 5 minus 16 is going to give me negative 11 plus 18I all over 5. Okay. Now, if I wanted to write this so it looked more similar to that complex number, so A plus BI, that form where we have the real number plus my imaginary part, I can write it as negative 11 fifths plus 18 fifths I. And a benefit of writing it in this form is if one part of your numerator would be able to simplify with the denominator, it allows you to do that. Now in this example, it doesn't help us simplify anything, and I'm not going to mark it wrong as if you leave it as a single fraction, but you do have the option of splitting it up into two terms and putting it in this form with the real number plus the imaginary part. Please let me know if you have any questions about complex numbers, simplifying complex numbers, or any of the operations with complex numbers.